Krupa Reddy, you can join one more time. Guys, let others join. Actually, like there is a power problem. Only I have just 35% of the battery in my laptop. So we'll see how long we can do it. Okay, last class now we have started with the optical OFC. WDM, that is wavelength division multiplexing. So that's what we have seen. So we have seen now what do you mean by WDM, that is wavelength division multiplexing, where we can, in a single fiber, we can send multiple wavelength lights. So our different colored slides, no, different wavelength data we can send through single fiber. That's the meaning of WDM. And we have seen different types of WDM. No, we have this. You can see this. This is 8-channel WDM. This is the commercially available WDM. We have 8 channels, 16 channels, and 32 channels, 64 channels WDM will be available. Again, based on requirement, we can send no different wavelength lights. And this is the different types of WDM technologies. We have thin film based WDM, fused fiber coupler based WDM, array waveguide based WDM, interleaver based WDM. These are the different frequencies, and we have seen uh, this is the WDM optical components. We have this laser source. This is the this from where we'll be getting different patterns of colors, the different wavelength signal will be getting. Then we have this Maxender interferometrics will be there. Then multiplexer. Again, this also is a multiplexer only. Maxender interferometrics. There is also Mux. Then we have this multiplexer where different wavelength data from different sources we can send through this multiplexer to the fiber. At the demultiplexer, we collect those things and we will send individually using local oscillator. You send it to this photo detector. From there, no, you can at the receiver you can transfer. That's what we have seen in the last class. Then the next topic was Maxender interferometrics. That topic I'll do it in the next class. So that is some big derivation is there, and the concept is a little tricky. So each one I was explained differently. So I'm skipping this Maxender interferometrics. Directly I'm going to this one in the next class I'll do it. So I'll go to this next topic is circulators and the optical isolator. See this. This is the optical isolator and circulator. So the next topic. Come back to this one. This is the optical isolator. Is a two-terminal device. Is a two-terminal device. Optical isolator is a two-terminal device. So it will be somewhere above here. You can see this. There is a laser source and the optical connector which connects your light source into optical fiber. There's optical cable, and there will be an optical isolator which isolates your source and destination. It's like whatever the signal, optical isolator will try to send the data. It allows your data to move only in one direction. You can see this isolator signal propagates only in one direction. Other direction, it blocks the data. We don't want when you send the data from laser source towards optical fiber at the receiver, and there is a chance that your data may come back. The light reflected may come back. Sometimes you'll get reflected data that may affect your source. To avoid that, we'll go for optical isolator. So optical isolator is a two-terminal device. So input will be there, output will be there. All the data will move in only one direction. This arrow represents data moves in only one direction, and other direction will try to block. You can see this. This is the structure of your optical isolator. Everyone can see this. It's you can unmute one or two. You can tell me. Yes, you can hear. Someone can unmute and can tell me. Yes, you guys are able to listen.
Yes, sir.
Okay. Thank you. This is the optical isolator. You can see three components are there. The three components: Birefringence wedge, Faraday's rotator, again birefringent wind. These are the three components of your optical isolator. So this birefringent wedge, it has, it will be like this. It has, it is made up of two different refractive index material. It has higher refractive index. When you send horizontal polarized signal, this horizontal polarized signal, when you send through this, through the, like higher refractive index material, it tries to bend in this 45-degree. Only horizontal signal will try to bend. That is called extraordinary ray. And whatever the vertical polarized signal, it tries to move in same direction. There won't be any bending. So again, I'll tell you one more time, I'll repeat it. This material, whatever the birefringent wedge, it is made up of two different materials. No, it will be having high refractive index and low refractive index material. When you send horizontal polarized signal, it tries to bend around 45-degree, or no, some based on the your refractive index, it will bend. That bended signal is called extraordinary ray. In the low refractive index, if you send vertical polarized signal, there won't be any bend, so data will try to move in same direction, right? You can see this. It has higher refractive index with the horizontal polarized signal, and the lower refractive index with the vertical polarized signal. So horizontal signals will try to bend, vertically polarized signal will try to move in same direction. And we have the second block, that is Faraday's rotator. This is a Faraday's rotator. Again, Faraday rotator, it is made up of magnetic field dense material. There will be a magnetic field dense material, and there will be a rotor, and some magnetic constant will be there. When you try to move any data, either it can be horizontal or vertically polarized signal, it tries to rotate your signal at 45-degree. Data will be rotated at 45-degree. So it's coming now. So data will try to rotate at 45-degree. That's what we are doing. So this is working of isolator. Before that, no, I'll just show you one video. I hope you can listen to this video. Optical isolator. Just go through this video. This is audible. This video you can watch. It's audible.
Yes, sir.
Okay, just see this one.
Hello everyone, this is Colin from Fiber Optics for Sale. In this video, I will explain what is a fiber optic isolator. So let's get started. The picture at the left shows some fiber optic isolator products. So what is a fiber optic isolator? Isolator is an optical component that allows the transmission of light in only one direction. The light is completely blocked in the other direction. Isolators are used to prevent unwanted feedback into lasers, so the laser's operation is not disturbed by the feedback from the fiber optic system. Now let's see how an isolator inside looks like. Here is the structure of a typical polarization-independent isolator. It is made of three parts: an input birefringent wedge, a Faraday rotator, and an output birefringent wedge. The blue color trace shows how light travels in the forward direction. Light traveling in the forward direction is split into two beams by the input birefringent wedge. These two beams' polarization is rotated by the Faraday rotator. Then these two beams are combined by the output birefringent wedge. Then light can now be coupled back into the fiber, and the continuous is traveling in the system. The red color shows how light travels in the backward direction. Light traveling in the backward direction is also separated into two beams by the output birefringent wedge. Then these two beams' polarization is rotated by the Faraday rotator. But when these two beams get to the input birefringent wedge, instead of being combined back into one beam, they are diverged even further apart and cannot be focused back to the fiber. Thus, the backward light is blocked. But if you want to truly understand how this works, you need to understand what is birefringence and what is Faraday rotator. So let's get started with birefringence. Light has polarization. Polarization is the vibration direction of its electric wave. For most materials, light's polarization doesn't matter. All components of the light are bent at the same angle and travel the same path. But there are some crystal materials, such as a calcite crystal, that have different refractive index for two perpendicular polarizations of the light. These crystals are called birefringent crystals. Birefringent crystals have lower refractive index for the ordinary ray, shown as the horizontal polarization O ray, so the light is bent less. They have higher refractive index for the extraordinary ray, shown as a vertical polarization E beam, and the light is bent more. In this way, those two polarizations are spatially separated at the output side. The birefringent wedge of the isolator uses this behavior to separate the O ray and the E ray. Now let's check what is a Faraday rotator. A Faraday rotator is an optical device that rotates the polarization of light due to the Faraday effect. Faraday effect is based on magneto-optic effect. In this picture, the light has a vertical polarization. After passing through the Faraday rotator, the polarization is rotated to an angle. This rotation angle depends on the magnetic flux density B, the length of the path D, and the material's verdict constant V. In fiber optic isolators, this rotation angle is chosen at 45 degrees. Faraday rotation is single direction only. If the light at angle beta travels at the backward direction, it will be rotated another B angle in the same direction. So now the angle becomes 2 beta. It will not be rotated back to the vertical direction. This single direction rotation makes fiber optic isolators possible. Now let's get back to the structure of a fiber optic isolator so we can take a closer look. Let's look at the forward direction first. The input light is separated by the input birefringent wedge into two beams. The O beam has a 90-degree vertical polarization and the E beam has a 0-degree horizontal polarization. After the Faraday rotator, both beams are rotated a 45-degree angle.
Here O is ordinary ray, and E is extraordinary ray. O is a vertically polarized. That's why it is moving in the same direction, and extraordinary ray there is a bend.
So the O beam is at 45 degrees and the E beam is at minus 45 degrees.
So after Faraday rotator, directly is moved from Faraday rotator around here, there is a shift. After Faraday rotator, there is a 45-degree shift. This is positive and this is negative.
The output birefringent wedge is cut at a different way than the input wedge. So its O beam is at 45 degrees and E beam at minus 45 degrees. So it combines its two beams back into one single beam. The light can continue traveling in the forward direction. Now let's look at the backward direction. Light travels backward is separated into 45-degree O beam and minus 45-degree E beam by the output wedge. Then these two beams are rotated again a 45 degree by the Faraday rotator. Now did you remember that the Faraday rotator rotates light in only one direction? So now the O beam is at 0 degree.
This is O beam here, positive 45, and E is minus 45. So when you send through this Faraday rotator, 45, again it will be in clockwise direction. So that's why it has become 0, 45 minus 45. Here already minus 45 is there. When it goes through this Faraday rotator, 45 minus 45, minus 45, minus 45. So it will become 90 degree. So this is where it has become vertical and this has become horizontal, but it is other way over here. You need to observe that.
And the E beam is at minus 90 degree. 0 degree degree is horizontal and minus 90 degree is vertical. So here is the tricky part. To the input wedge, now the O beam becomes its E beam since it is at horizontal. And the E beam becomes input wedge O beam because it's now vertical. That is why the Faraday rotator is chosen at 45 degree. So now you can see that light follow the same path inside the input batch. The E-beam follows original E-beam direction, and the O-beam follows the original O-beam direction. Only this time, instead